So the meeting ended abruptly, so that's why I have to start a completely fresh session. I hope my voice is audible to everyone. Okay, great. So let me share the screen one more time, and again I'll explain the story from scratch. Is the screen visible? Okay, great. So let me clear the screen. We discussed what we have discussed in the earlier half was like what is the free lunch concept, how it is changed, how the hardware with multiple cores make people write a fresh program. Now, when the multiple hardware resources have been used to the extent that they can be parallelized, some drawbacks appear. So let's say this we have two programs. What we are understanding is what happens when you people are exploiting the hardware capability and executing multiple programs at the same time. When these programs are not depending on a common thing, then it is fine. But as soon as there is a dependency or there is some sharing between the two programs, then the problem starts happening. So let's say we have both programs can execute at the same time. Now, let's say there is also something called as a store or warehouse. There is a concept of warehouse, and this warehouse have number of goods, and it keeps the log of how many goods are stored in this warehouse. So it have a log of it. So like initially in this warehouse there are four goods. Number of four goods are available. So what producer is going to do is producer is going to produce a good plus, and then it will add that good into the warehouse. It will store the good into the warehouse, and the consumer is going to take a good and consume it. So consumer will say minus the good, and producer will say plus the goods available. The producer is going to add the resource. 1 minute. मी ह्याच्यावरनं गेलो डेटावरनं गेला लागलोय बंद पडलंय त्यासाठी फोन केला बोलवलंय बघूया की
त्याला कसं माझं काही जास्त दिवस नाही
Somebody's mic is on mute. Please mute the mic.
अरे ते
And consumer will say consume the good. It will say minus. So the good will be consumed from the warehouse. Now, the strange thing may happen. Let's say there are 4 goods available currently. So when producer produces a good, it is adding goods or it is adding the resource. And when consumer consumes, it is decreasing the resource or decreasing the number of goods. So let's say producer read the value from the log or it created a good. So when producer has to submit the produced good to the log or to the warehouse, it gets the number of existing goods, which are 4. It will say plus 1 good I have created. So total number of good is 5. And it will try to write this 5 into the log. So log must be updated to 5 as soon as 1 good is produced. When the consumer comes in picture, it reads the present value, which is 5. Then it will say, I am going to consume 1 good, and the latest count or the new count of the good will be 4. So the consumer will come and it will write the value as 4. So one producer cycle and one consumer cycle will lead to the log value matching to the original log value before the operation of a producer and a consumer. Doesn't matter in which order we execute this, the final result, end result will come as 4. For example, let's say if the consumer goes first, you will set the value 4 minus 1 to 3, and then producer will come in picture, and producer will say 3 plus 1 is equal to 4. So one producer and one consumer sets the value of a log or sets the value of a total goods available to the same before the operation. This will happen if you execute the operation in serial order, and doesn't matter in which serial order you are executing, whether you are executing producer at the first or consumer at the first, the end result will remain same. That is, number of goods available in the log, the number of goods available in the warehouse will be 4. Now what could go wrong? As the both programs are running at the same time on different CPUs, different cores, as the both programs are running at the same time on different cores, let's say, let me diagram a bit. Let's say when the producer is executing and consumer is executing, they both read the same value. The producer got the value of log as 4, and the consumer also gets the value of log as 4. Why this is possible? Because as both programs are executing on 2 separate cores, they are executing at the same time moment. So if both the programs, that is the producer and consumer, reads the value of this log variable, then both will get the current value, which is 4. Now trickier part happens if producer produce and consumer consumes. The consumer will have value as 3 and the producer will have a value as 5, end value as 5. Now let's say if producer writes this 5 value to the log, then log will be updated to 5. Then consumer's value will be overwritten to the existing log value. So the log value becomes 3. Now this is inconsistent because still we have executed only one consumer and one producer. So in this case, because both programs are reading the value of a variable at the same time, the end result is not consistent, or end result is not the result which will appear if we execute the producer and consumer in serial order. So we can't rely on this result. What if the consumer executes first and the producer executes second? In this case, the consumer will write the value 3 first, then the 5, the producer writes its own value, which is 5, and the end result will be 5. So again, reversing whether the producer executes or the consumer executes, the end result is not consistent. And why this is happening is because both programs are executing at the same time, and both programs read the value of log variable at the same time, which was 4. And this is not matching with what will happen if you execute the program in serial order. So when we execute program in a parallel order, we have to make sure that the end result of the program should match to the execution of a serial order. That is a consistent execution. This particular condition have one name in OS. We refer this scenario, this case, whatever we have discussed now, we refer this scenario with one word in operating system. Can anyone tell me what this scenario is called as? You can type your answer in chat box. This scenario that we have discussed have one name in operating system world. Yeah, this is not only race condition. So here, producer and consumer are rushing for a resource called as a log. or a goods number of goods available. And as both producer and consumer rush for the resource, then it will generate a race condition. So can you recall from the operating system syllabus what is the solution proposed to this race condition? What is the first solution that has been proposed by the operating system to handle this race condition? Aditya, your answer is very correct. Aging, critical section. Okay, anything else? So I have two answers. One is from Sakshi, which is aging, and second is critical section by Aditya. Any other answer? How the OS will handle this? Semaphores. Okay, this is the answer by Pratham is saying locks. Okay, good. Any other answer? I have four answers with me. One is aging, then the second is critical section, then the third is semaphore, and then there is locks. Okay, so serialize access. This is by Siddhi Patil. Okay. Mutual exclusion by Mitali. Okay, so lot of OS concepts. Now see, we are learning APL, Advanced Programming Laboratory, and these all concepts belongs to the operating system, right? So we are actually going to implement all of these concepts in here. So we are going to implement locking, we are going to implement with this mutual exclusion or the critical section, whatever you are saying. Then there is a concept called as semaphore, then there is a word called as lock, serialized access, and one word which is not yet written by anyone is called as monitor, right? So these are the some concepts that are from the OS, and we are going to implement all of them one by one. So here I want to bring your focus on one thing that I iterated earlier. Like one technology solution always solves one problem and creates another one, and then you have to solve that another problem, and the process continues, right? So see, to improve the efficiency of the overall system, people added multiple CPUs to the system, and now you have multiple CPUs to the system. It has created a problem called as race condition. The very early solution to the race condition was locks. I hope my voice is audible to everyone. The very early solution to this particular problem of race condition was locks. So let me use a blank scenario to explain how locks work. So let's say, thank you Sakshi for replying. So let's say we have resource. We have a resource. Now this diagram is representing the resource. Let me call it as R. And we have also a program P1, and we have also a program called as P2, and these both programs need to use this resource. And if these both programs use this resource at the same time, that will generate a race condition. Now, a trick here is they can't use the resource at the same time because there is a locking mechanism. As you can see, this resource is put into a box. Let's assume this box is a lock. This box is a lock. So, and when this will get locked, as soon as one process enters the system, this lock will get placed. And as soon as this process exits the system, this lock will be released. So when one process enters, the lock will be placed, so nobody will be enter into the system. And as soon as the process exits, the lock will be released, so the next process can enter to the system. Hence, what happens is, as this resource is closely locked and monitored, and only one process can enter to the system, this solves the problem of race condition. So let's say that this resource have a value of 4 again, and we have one producer and one consumer. So let's say that consumer entered to the system and it locked it. So it gets the value of resource as 4. So consumer got the value as 4. It will consume the value and it will set it to 3. Now the value 3 will be returned to the system, and then P2 will exit and the lock will be released. Then producer will enter to the system, and first thing it will do, it will lock the system. As soon as the lock is placed, now nobody can enter. Now it will read the value of the resource. Now the value of the resource is 3. Then it will produce a good, and the new value, which is 4, will be placed in the system. Then the producer will exit and the lock will be released. Now a new producer or a consumer may enter into the system, but the value of the resource will never enter into a race condition. So that is a benefit of a lock. Are we clear what is the benefit of a lock? Okay. Now, before writing a program, so we will immediately write a program to create a lock. How we will see how to put a lock on a resource in Java. Before proceeding with locking implementation, let's see one more scenario. Let's see one more scenario. So what we will do is, let me create a completely new file. Let me say that you people have one lock with one resource, and also you have another lock. Okay, this is the wrong thing. You have another lock and another resource. So let's call this first lock as resource 1, and let's call this lock as resource 2. And again, we'll have one producer and one consumer. So to use a resource, the process must enter into the system and then lock it. So let's say that the consumer entered into the resource 1 and producer enters into the resource 2 and then locked the resources. Now after this, consumer needs resource 2. It needs access to the resource 2, and producer needs access to the resource 1. Now each of the resource is locked by other process. That is, the producer needs a resource which is locked by consumer, and the consumer needs a resource which is locked by producer, and neither of them can finish their job. Also, as they are not able to finish the job, they will not release the resource that they are holding. That is, consumer is holding R1, so it will not release it, and the producer is holding R2, so it will not release it. And as R1 and R2 both are locked, they are required by other process, there is a deadlock. There is a deadlock. Can anyone write in the chat box what this condition is called as in OS? This scenario is called as a deadlock, of course. But this scenario appears, the deadlock appears in the system when what we have. What is the condition for a deadlock? When we say that, okay, this is a deadlock. Can anybody tell me what is the wording used by the operating system? What is a deadlock? So as soon as I start writing wait, I got one answer, which is circular wait, hold wait, waiting state. Okay, when both processes wait for infinite time. Okay, hold and wait. So we call this as a hold wait or a circular wait. So whenever we have a circular wait, we call this condition as a deadlock. Why circular wait? If we simplify the diagram, we have a P1 which holds R1, let's say, assume that it holds R1, which is required by consumer. Consumer holds R2, R2, which is required by P1. So it forms a vicious circle, like, and nobody will be able to exit this circle. So this is a circular wait. That P1 holds a R1, which is required by C1, and C1 holds R2, which is required by P1, and the circular wait gets formed. And as soon as circular wait gets formed, the locking, as you will release the resource only if your job is done. Now neither P1 will be able to complete a job, neither C1 will be able to complete a job, and they will be in a circular wait. So what is the solution proposed by the OS for this problem? What is the first solution that has been proposed by the OS for this? In the literature, of course. Sorry. Can anyone tell me what is the first solution proposed by the OS for this solution? So see, we are going to implement the solutions also. So can anyone still write what is the solution? If you are typing, you can unmute and say what is the solution. Okay, so the initial solution proposed on this problem was locking the resources in a serial order. That means when P1 needs both resources R1 and R2, then P1 must lock these resources in one order. That is, it must lock R1 first. If it gets the lock on R1, then only it can lock R2. Unless and until a process have a lock on R1, the process can't get lock on R2. The same thing will be true for C, that if C wants to lock the resource, C must lock first R1. And if C gets a lock on R1, then only the C will be allowed to lock R2. Now, let's say one of this process gets a chance to lock R1. So if let's say producer locks the R1, then it will be able to lock R2. And as C tries to enter to the lock of R1, but as it has been already been acquired by the producer, C will not be able to enter into the system. And the deadlock problem will be solved. The circular rate problem will be solved. But it will create another problem. Can anyone tell me locking the resources in a serial order? This we call this as a serialized lock. Serialized locking. Can anyone tell me what is the problem of serialized locking? That if you want to lock R2, you must get lock on R1. So that is a serial order. So let's say you have 10 resources, you need 10th resource, then you must acquire lock on R1, R2, R3, R4, up to R9. Then you can get a lock on R10. Unless and until you have lock on all the resources, that is from R1 to R9, you won't be able to get a lock on R10. So can anyone tell me what is the drawback of the system? In chat box, quick answers, or you can unmute yourself and tell me the answer. Am I audible? Okay. I thought again I've lost the connection. So can anyone tell me what is the drawback of the solution that we just seen? Like we will log the resources in the serial order. What could be the drawback of this? Okay, resources may be blocked forever. It will work as starvation. It would create a starvation. Okay, nice answer that it will create a starvation. That is another thing. But resources may be blocked forever. That is not the case. See, what will happen is P1 will start engaging the resources R1, then it will engage R2. As soon as it gets lock on all the resources which are required, then P1 will finish its job. As soon as P1 finishes the job, it will start releasing the lock. So when P1 releases the lock, then C can start acquiring the lock from the R1 to R2, and then C1 will finish the job. When C1 finishes the job, then the new process can come up and then start acquiring the lock from R1 to whatever number it needs. So of course, this resources will not be locked forever, but it would create a starvation. Any other answer? So Sakshi, your half part of the answer is correct, but it won't create a forever blocked scenario. Any other answer? Okay, good. Any other answer? The starvation situation is a really correct answer, but any other answer? Still, I need one more answer. Any other thing? Can anyone tell me? So, okay, let's see the answer. So, I'll use the right side. So, let's say you have 100 resources, R1, R2, R3, R4, R5, up to 100. If you have 100 resources, if you have 100 resources, and if you start locking the resources from top to bottom, if you start locking the resources from top to bottom, and if you need only 99th resource, your process needs only one resource, which is resource number 99. The rest of the resources, which are from 1 to 98, are not required by your process. You need only one resource, which is 99. But what your computer has to do is, or what your process has to do is, it has to start acquiring the lock on all the resources. So it will altogether lock all the resources between 1 to 98, and then it will acquire a lock on 99th resource, and then will use it. What if another process needs only the third resource? What if there is another process which needs only fifth resource? What if there is another process which need only first resource? So as because this C1 process needs the 90th resource, and we have implemented a locking mechanism which will go in a serial order from top to bottom way. To avoid a deadlock, we implemented a serialized way of locking, and we are going from top to bottom order. As this C1, some process is going to acquire need a 99th resource, it is going to lock all 98 resources before locking the 99th resource, will starve other processes. So this is not an efficient way of locking. This is not an efficient way of locking. Now we are talking only about 100 resources. What about if you have 1,000 resources of different sort? You have to lock all 999 resources to get a lock on 1,000th resource. So this is not an efficient way of locking. But at the same time, you want to avoid deadlock. You want to avoid deadlock. So here comes the monitor in picture. Then monitor also have a drawback. Then comes the semaphore, right? So this is the evolution. Like you first to make use of new hardware which have multiple cores on a single chip. The people come up with a thing called as parallel processing or multi-threading or multi-processing. The multi-processing thing triggered a problem called as a race condition. To solve the race condition, people come up with the solution called as lock. The locking mechanism created a problem called as deadlock. Then people come up with the serialized locking. Then serialized locking have its own problem. Then people come up with something called as a monitor. We'll see what is a monitor in detail. Then monitor have its own limitations, so people come up with the semaphore, and so on and so on and so on. So we are going to see all the things. We are going to implement the lock. We are going to see. We have seen threads in the last session. We are going to create a race condition now. Then we'll solve the race condition using lock. After that, we will create a deadlock, and then we'll solve the deadlock using serialized locking and then monitor. So that is how we are going to implement. So let's start with the threading program, and let's create a race condition. Intentionally, we'll create a race condition. We'll solve the race condition using locking. Any doubts before starting program? Any doubts till the moment before we start programming? If you have a doubt, you can ask. Am I audible? Very important question. Okay, great. So let's start writing the program. So this is what we are going to do in the threading section from start to end. Okay, this was the program that we have done. So let's create a completely new program, new file. Let's save this file as racecondition.java. See racecondition.java, fine. So public class race condition, and this will act as an entry point for our program. Now we need a resource, let's say we have a resource called as resource. It's an integer variable, and let's say its value is 1. Then what we are going to do is we are going to let's treat this resource as a good, consumer good. So producer will increase the resource by 1 and the consumer will consume the resource by 1. Now we are going to create a thread. So first important thing is let my class say extends thread. There are other ways, we will explore the other ways one by one. So right now I'm going to make use of extends mechanism. So my class, which is going to create a thread, will say extends thread, which is a class from util lang package. So it will allow me to create a thread. Now we have seen in the last lecture that if I want to run anything as in a thread, I must write that code inside a run method, or I should call the method that I want to run as in a thread by using run method. Now the code which will consume the resource, we will write that code inside run method. So let's say I will create two objects of this class. So race C, let's say producer P is equal to new race C. So what job we expect by this producer is, so if I say p dot start, writing p dot start will start execution of a run method. Now this p, let's say, indicates producer. So what I want is inside this run method, when I say start using p, the resource value should get incremented by 1. And let's say it will be incrementing infinitely. So what I'll do is, I'll say resource plus plus. So I'm incrementing the value of a resource by 1 time. I want this code to execute infinitely. So I'll say while 1. Now this resource will be produced infinitely. Right. Now let's create a second thread. Race condition. Let's call this as consumer and let's say new race T. Race condition. Now again let's start the thread. So again when we say c dot start, the same code will execute. Right, but I don't want to increase the resource. Now I want to decrease the resource, but that is not going to happen because p dot start will call the run method. Also c dot start will call the run method, and in the run method right now we have an infinite loop which is incrementing the resource by 1 each time. So this is not a key, this is not going to work. So what we have to do is, if the p dot start is entering inside the run method, then the resource must be increased, and if c dot start, that is a consumer start, entering into the run method, then resource must get minused. To handle that, I'll take the help of a flag. So I'll say boolean flag, and initially let's not initialize the value. Let's say boolean flag, and p dot flag will be set to true, and c dot flag will be set to false. Now we have to check the run method. Let's say if flag is equal to flag, that means the flag is true. If the flag is true, means who is setting the flag to true? The resource incrementing, that is producer. So in this case, I want to produce a resource. So I will start incrementing the value of a resource infinitely. And if the flag is false, the flag is false for the consumer. So in the case of false, I want to minus the resource by 1. And again, this must execute infinitely. Twice again, I'll say while true. So 1 producer and 1 consumer. Now there is no output on the screen. So what we will do is we'll output the value of resource immediately on the screen. System.out.println. Let's say resource. I'll put an opening bracket and closing bracket for while. The same thing I'll do for the else block. Let's put an opening bracket and let's put a closing bracket, and let's say out.println resource. right? So this is our setup. So we are printing the value of resource after incrementing as well as after decrementing. And there are two threads which will start, one for the producer and one for the consumer. Let's try to compile this program and execute. Hopefully this will compile. Oh, I'm not in the proper directory. Let me go to cd my software projects, my Java, cd thr, Java C, race condition.java, compiled, and let's say res. So now let me terminate. Now here you can see some random values. Like, so it's not possible to see who is generating what value. So another thing we will do is we'll print the ID of the thread which is doing it. So what I'll do is I'll say here producer, and I'll get the ID is equal to this dot get ID is the method that I can use. And then I'll say R is equal to the resource, right? And on the same line, in the same way, what I can do is, let me copy this. Instead of producer, I'll get the word as consumer, right? So let me recompile and run. Now let me terminate the program. Here you can see that the producer executed and its value was 513 and 514. So it is very consistent value. Like 13 was the original value, and after that, if you are executing producer again, the value must be 514. But just before that, you can see that the consumer has executed and its value is minus 597. Obviously, these values are not in sync. The value of the consumer and the value of producer are out of sync, right? So even if we have a, so this is not a common resource. Let me make use of a static. So what will happen is the static variable makes sure that the both objects have the same value. So this was a, like what we can say, a loophole in the program that I created, because as the resource was not static, method have each method have its own value of a resource. So it was highly inconsistent. So what we will do is now the resources will made static. Let me compile again and let me execute this condition. Okay, so now the values are mostly in sync. So we have to find the loophole where the values did go in out of scope or out of sync. Yeah, here I can see that. See, so consumer consumed 107. Here again, consumer has consumed the value, but the value of the resource is still 107, whereas the expected value after one consumption must be 106. On the next consumption, however, the value has become 106. After that, 105, then 104. After this 1/0th consumption, you can see that the value by the producer has become 108. And again, you are consuming 103. Again, you are consuming, which is 103. Again, you are producing is 104. So here we have a sync thing, which is reduced, consumed is 103 and produces 104. But again, you consume and the resource become 102. And again, you are producing, it becomes 103. So here, the value of the resource is not in synchronized order, right? So you are getting a race condition here because the producer and consumer threads are modifying the same resource. You are getting some difference in continuity or inconsistency in the output. Did you see the race condition? Neil, you can break the program by simply pressing Control C. It will take out your program from the infinite loop, no problem. I am replying to Neil on the chat window. Okay, fine. So did everyone got the concept of race condition? We are going to solve the race condition immediately. Of course, by putting locks. Okay, great. Any doubts? So let's start putting out locks on the threads. So To put a lock on a thread, what I'll do is in Java, there is a word called as synchronized, right? So synchronized can lock a resource. The synchronized call is specialized in locking the object. So here what has happened is this resource, int resource, this is a variable, this is not an object. Whereas the locking in the Java can lock the object and not a variable, independent variable, which is like a data type or what we can say, a non-reference variable to be very specific. So I will change the setup a bit. What I'll do is in the here, I'll say class resource. I'll create a new class called as resource. And this class will have a variable called as R. Initially, it won't have any value. So this is my class, right? And I have two methods. Now I need to create two methods. So one thing is a resource. Now I need a producer. I need a producer. So what I'll do is I'll say class producer extends thread. And we know that this producer class, which is extending a thread, now can have a run method. And in run method, what we want, I want this thing to execute infinitely. So in the producers run method, I want resource to be implemented infinitely, right? Now I need another class which is going to consume the resource. So I'll say class consumer extends thread. Again, it is extending a thread, so it can have a run method. And what we want from the consumer, we want consumer to consume the value and print it on the screen. So my producer and consumer are ready. Instead of using a resource, now I want this object of this class to be used. The class is resource, right? So let me clear out the run method, which is from my main method class. Now the setup is becoming very simple. Now what we will do is I'll say resource, which is my class, have an object, let's say R1. And here I will initialize this object. R1 is equal to new resource. And we will pass this same object R1 to consumer as well as to producer. Now I don't need this flag. I'll remove this flag variable. Now this both producer and consumer method are still sharing the same resource called as R1 of class resource, which have one static variable, which is R. Now let's put out a constructor for consumer. See, you are calling a parameterized constructor for resources for class race condition, right? And instead of race condition class, of course, this change need, I need to write producer here. So now if I want to create a producer thread, I must create an object of producer. And now if I want to create a consumer thread, I must create an object of consumer thread. Now I'm calling the parameterized constructor of producer and consumer. I must satisfy this constructor. Otherwise, I'll get a error during compilation. So I need a constructor which can handle resource class. And in this, I'll simply say resource is equal to R. And here I shall write inside the constructor setup, I'll write R is equal to R1. The same thing is required by producer. So public producer resource R1. And here R is equal to R1. Again, let me declare a resource R. So let's understand what is the setup before executing the program. So you have created one common resource in your main method, and you are passing this common resource to both producer and consumer. As you are passing an object of a resource class, your both class consumer and class producer must have a constructor which can accept a resource of type R. So here, the value that you pass here, R1, will be copied in the constructor, and then you are assigning this constructor value, variable value, to the class consumer value, R. And now here, you can say R dot R minus minus. R, let's say R dot goods is the variable, minus minus. So another change is required is, I will call this as goods. So here, R is the resource object, and you are saying R dot goods minus minus. So resource has been consumed. The same thing is required in producer class, R dot goods plus plus. So you are incrementing the resource. So R dot goods, right? R dot goods, and we are printing the value of resource. As I'm using the same object, single object, I really do not need to make it static. See, I am using one object in both producer and consumer. So I don't need to make the method as the variable as static, because I'm using the same object. If I'm making a use of two separate objects, then I should have made this resource as static to share it among multiple objects. But as I'm using only one object of resource class, there is no need to make the resource as static. So this is the setup. Again, we will go into a race condition, because this is the bit different setup. Let me compile the program. Java C race condition Java. Okay, error. Fine. File run. Yeah. So this is the problem culprit. Okay, variable R cannot be referenced from a static context. Let me clear this also. What is the R1? Resource R1 is been created. Yeah. So clear Java C and race condition. Again, we have this race condition because both programs are sharing the same value. See, producer has produced to 1 minus 1, and consumer is saying minus 2, 3, so the consumer 3, then 2, and again consumer, but the value has become 3, and again consumer, but the value has become minus 4. So incrementing and decrementing not in sync. So now we will need to put a lock. To put a lock, I'm going to make use of a call called as synchronize. So in Java, there is something called as synchronize. Now here, I can synchronize this R before entering to the system. So as soon as I say synchronize R, that means I am putting a lock on R. Right? And this is an object reference. This R is an object reference. So if you are putting a lock on R, this R of consumer and this R of producer are same. So if one process is entering only by locking the resource, that means the other process cannot enter inside that resource. So here we are implementing that locking scenario. So let me lock the resource R in the consumer also. Sorry, producer also. So we have locked the resource in consumer. Now we are locking the resource in producer. So producer has locked it. So this is for while, this is for synchronized. And now let me try to compile. Compiles, and now if I execute and if I terminate the program at any time, now you can see that consumption is in sync. 17, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8. I need to go and find a producer, whether there is a producer or not. So producer has not got a chance to execute. Okay, here is the producer. Producer, the last value by the producer was 1432. See how wonderful sync it is. Like 1432 was the last value by the producer, and the consumer has exactly deducted the value by 1. So it assures us that the producer and consumer are going in sync, and the values of the resource will be in consistent order. Doesn't matter who executes, whether the producer or consumer. Now I really do not have a control on the program, whether the producer will execute or the consumer execute. Right now I do not have control, but we can manage this, how many times a producer can execute and consumer can execute. Now this is a very good example of starvation. When the producer was executing, only producer has executed and the consumer was starved. And when the consumer execution started, only consumer is executing and the producer is starved. So this is not a fair execution, but we have solved the problem of race condition. So even if we are not having a fair execution between the producer and consumer, what we have achieved is we have solved the problem of risk condition. So our program is in resource is in a consistent state, and the risk condition is solved. So here again you can verify. So let's see what is the last value by producer, which is 1024, and then consumer starts, so it becomes 1023, and so on. So if you randomly pick any value, we will be sure that the value is in sync and consistent. Any doubts? Did you see the execution of the program? Am I audible? Okay. Okay. So a quick poll is coming, and I will upload this program on Moodle for the reference. And in the next session, we will start with putting out, we will make sure that the producer and consumer will not starve. We will see how to stop starvation of the threads. And then we'll see what is the drawback of locking and synchronizing. We haven't seen deadlock. So first thing we will do in the next session is create a deadlock and then a monitor, and then we will have to solve the starvation problem and so on and so on. So before that, let me conduct a quick poll based on whatever we have done in the session. A quick poll. You have only 2 minutes to answer this, and only two options. So one is correct answer and one is a wrong answer. Attempt the poll immediately. So this is the result. See, this was when I came across this situation. It was during one of the Viva. So the examiner was asking what is the data type of a variable which can be locked with the synchronized, right? So any kind of a data type variable will be locked if it is referring to a reference type. If the data type is a value type, then it won't be able to lock that resource. So here the both answers are, first answer is absolutely correct. The synchronize will lock object, and the B answer is partially correct. The B answer is correct only if the data type that you are representing right now is belonging to the reference type. If the data type that we refer to lock, it belongs to the value type, then the answer is wrong, right? So if you came across this kind of a question, make sure that if you answer like the synchronize will be able to lock only the things which belongs to the reference type things. Okay, so you can quit the session. See you in the next session. And by today 2 p.m. you will get a task on Moodle. Those who have missed the first task, yesterday's task, must attempt this today's task. The task will be available by 2 p.m. and you must complete it by 4 p.m. It is for those who missed the yesterday's task. Okay, you can leave.